Hello, this video is the start of a new tutorial of Google Earth Engine. Instead of starting with an introduction to GEE, I decided to start with a case study application to illustrate the value added of such system. The case study includes the calculation of vegetation area in one of Egypt's provinces, Sharqeya province, using Google Earth Engine. Content of this lecture are as follow. First, what is Google Earth Engine? Second, uploading area of interest boundaries, the Sharqeya province shapefile. Third, calculating NDVI for Sharqeya province. Fourth, extracting NDVI raster. And fifth, calculating area of vegetation. First, what is Google Earth Engine? This lecture is not intended to be a comprehensive introduction to Google Earth Engine. However, I'll just go over a brief description of what Google Earth Engine is. So Google Earth Engine is a cloud-based platform for Earth data analysis. It stores petabytes of archived satellite imagery and raster data and enable users to perform analyses on these data on the server side through APIs, both JavaScript and Python, and using huge computing power. Some of the potential applications are environmental monitoring, earth science, deforestation, etc. And this is the address of Google Earth Engine. If we go to that page, we'll find an introductory video here and a graph that shows that you couple satellite imagery with your algorithms, you build real-world applications, and you can click to learn more. Here are some case studies using global scale insights, using if you are working on a global scale phenomena. Ready to use datasets, so you can explore the datasets that are available here. The API, simple yet powerful API. So the Earth Engine API is available in Python and JavaScript, making it easy to harness the power of Google Cloud for your own geospatial analysis. However, the JavaScript is built in, it's built in the system. The Python API, you need to use a notebook like Google Colab or Jupyter. Yeah, here it shows the interface. We are going to explain that shortly. And here are some case studies of scientific and humanitarian impact. The most important part of this page is the sign up now button. If you don't have an account, you need to click here and sign up, and you'll get an email in 1 or 2 days giving you a link to your page. It has to be clear that you cannot use Google Earth Engine unless you sign up. This is the main interface of Google Earth Engine. It's composed of 5 main elements. The first element is the side window, and it contains 3 tabs: scripts, docs, and assets. The scripts tab includes a table of contents showing a list of all the scripts that you have written or the example scripts and so on. So it's just a table of contents of scripts. You click on the script and you get it on the second element, which is the code editor window. The second tab is the docs, and when you click on the second tab, the docs tab, you get a complete manual that will show you how to use different commands. So you can look for a specific command and get how it's used. You can get all the information related to that command. The third tab is the assets tab, and this is where you upload your own shapefiles or boundaries or images and so on. So assets are basically objects that you upload into the system, into the cloud, in order to use them in your application. The second window is the code editor window, and it works, code that you write here has to be in JavaScript. There is another way to use the API. There is another API apart from the JavaScript, which is the Python API. However, that API needs a notebook, as I said before. It needs Google Colab or similar. You can get a link to that code and send it, share it, or you can save it or you can run the code, you can reset the window, and you can play with the settings here. The third element is a side window that has 3 tabs: Inspector, Console, and Tasks. The Inspector is basically an identifier window. So when you click on that tab, the cursor turns into a cross, and you can click anywhere on the map viewer screen, and it will give you the value of the pixels that you are clicking on. The second tab is a console, and this is where you get the results of your code if you are writing a code that will generate a graph or text output. And the third tab is a tasks tab, and this is where it waits for your action if you are loading an asset, or if you are writing data, you are outputting data to your Google Drive or to the cloud. So this is the tab where you see the action for this one. So the fourth element is the map viewer window, and the map viewer window will actually display the results of your code if you are loading data, processing data, and producing analysis. So the result of the analysis will be displayed here if you use map add layer, and you can always fill the screen with the map viewer. There is a button here that will fill the screen. You can toggle full screen on and off, and you can manipulate the layers using the layers button. You can change the symbology, you can change the visibility, and the base map is actually Google Maps or Google Satellite. You can also draw some vectors: point, line, polygon, or rectangle. You can use these in order to identify your area of interest if you want to. The fifth element is the text box, the search text box, which has also 2 buttons, a search button and another button that will enable you to access the catalog that does not appear here, that second button. It's an arrow that you can click and access the data catalog. You can also search for datasets or places here. You can write the name of the dataset. If you write Sentinel, for example, you get all the Sentinel data available to you. This is a very important button, and usually this is where you start by looking for datasets. Now I'm going to go for a demonstration running the code to calculate the vegetation area in Sharqeya province. This is the interface as I have described it. So you have a window, a side window that contains 3 tabs: scripts, docs, and assets. And you have a table of contents, and then you have the code editor window, and you have the console window, the side window that contains the inspector, console, and tasks, and you have map viewer window. And here you have the search input box, and you have side button that enable you to access the data catalog. Okay, I'm going to run the code, and then in the remaining part of the lecture, I'm going to explain the different parts. So if you want to run the code, you just click run. So here you go. You have the vegetation area for the Sharqeya province is 3,234 kilometers. Square kilometers, or 769,877.3 feddans. The feddan is almost an acre. It's like an acre. It's a measurement area measurement unit that is used in Egypt, and this area calculation is for the period of January 1st, 2019 to December 31st of 2019. So it's 19. Okay, and as we are going to see, you can set the date that you are looking for to different dates. And that's it. Now, the efficiency of the code is that you have just calculated the area, the vegetation area of a complete province in just half a minute. So let's dissect the code and see the different parts of it. The second point in the lecture is the first part of the code, which is uploading the area of interest boundary shapefile. So steps to upload the area of interest boundaries. First, you go to the side window and you click on the Assets tab, and then you click New and you choose Shapefiles. Once you click Shapefiles, you will be requested to upload the 4 components of the shapefile, the 4 files, SHP, SHX, DBF, PRG, or the zip file which has all the 4 files compressed. Once you click here, you will be presented with another dialog box. That dialog box has a select button. You click on the select button and you either upload the 4 components, the 4 files that make a shapefile, or a zip file containing all the 4 components. And then you give it a name and you click upload. Once we have the file, we right click on the properties and this is what we get. So this is the asset ID or the table ID. You can actually copy it by clicking here and then you use it in your code, and it shows you the geometrical footprint of the asset you have just uploaded, and it shows you the location of that asset in relation to the world in red. This is the code. So the first part, get the Sharqeya governorate boundary. That's a comment just to make sure that I will remember what that code means after a while, because obviously I'm going to forget, or if someone else is going to read the code, he's going to find out what did I do with this code by just reading the comment above. So I'm creating a new variable called region, and then I'm storing the Sharqeya shapefile as a feature collection into that variable region. And the second line, I'm adding that region variable as a layer into the map viewer. So map, add layer, and you give it the name of the variable that you just stored the shapefile into it. And this is what you get when you use the map, add layer function. Obviously, there is one more thing that I did not show in this code, which is the zoom. And I'm going to show it to you when I start writing the code. Okay, so I started a new script, and then I'm going to paste the first step, the first part of the first step. The first step is composed of 2 sections. The first section is vector, loading the vector boundary of area of interest. The second section of the first step would be to load the Sentinel data. So first, the first line, as I said, is actually loading the shapefile that we have uploaded into an asset, and then we have stored that shapefile into a variable called region. And the second line is we add that region into the map viewer as a layer. We use the function add layer on a map, and the parameter of that function is the variable region, which stores the area of interest boundaries. And then one more step that I have not discussed, which is the zooming. So we use the center object function on the map, and we give it the object is region, which stores the area of interest boundaries, and we give it a zoom level 10. Obviously, you can play around with the zoom level using trial and error. So let's run this part of the script and see what happens. And you see here the progress bar. Okay, so this is basically the area of interest. And as I said before, I can actually fill the screen with the map by clicking on that button. I can go back by clicking again on the same button. So I can toggle the size of the screen, toggle full screen view. Okay, so that was the first section of step number 1. Let's go back to the lecture and we go to step number 2. Section 2 of step 1 is adding the Sentinel 2 level 2A imagery archive to the map. So in order to do that, we get the Sentinel 2 image archive, and we store that image archive into a variable. I called it S2. You can call it whatever you want. And I will show you how did I get this portion of the code, the image collection address or name. And then I'm going to use this image collection and filter it and store the filtered into a new variable. So I create a new variable and put the image collection into it, and then apply 3 filters to it. The first filter is filter by date, and I put the first date and the last date. So that's the duration that I want the imagery to be filtered at. And the second filter is a boundary filter. So I implement a filter bounds function, and the parameter is region. So this is the area of interest boundary. And the third filter is a metadata filter, and metadata contain many variables related, of course, to the Sentinel-2 imagery. Every type of image has different type of metadata. And I pick one variable from these metadata, which is called cloudy pixel percentage, and I use an operator less than, and I put a value of 1. So basically what I want is I want it to filter out all the images that have cloudy pixel percentage more than 1, and only get the ones that are less than 1% cloud cover, that have less than 1% cloud cover. The last function that I'm using on this filtered image collection is the median. Now, because we have so many images, probably close to 20 images per year, so I have 20 values for each pixel. So I'm picking the median value. So I go through all these 20 values that I'm collecting for each pixel, and I'm picking only the median and storing it in the filter. So the filtered is a variable that holds the image archive, the image collection, and then applies 3 filters, and then picks the median of the values here, and then picks the median of the values here. And then I add the resultant raster image here using a map add layer function. And the map add layer takes the filtered, but then again I'm applying another function, which is the clip function, and it takes the area of interest, the region, which has the boundaries of the province, and I'm clipping the filtered raster image by the area of interest boundaries, and then I'm stretching it using min and max values, and I'm using a band ordering, so I'm having band 432 RGB in order to generate a natural color composite. And this is the resultant image. It's a natural color composite of the Sharqeya. And this is the median value again. So I'm picking the median value of the year-round images collected for Sharqeya, and I'm making a composite here. Let's see how we do that in code. I'm going to paste the portion of the code. Okay, so this section is the second section of step 1, which is get the Sentinel image collection, Sentinel-2. So var S2 is the name of the variable. You can pick whatever name you want. It's probably better be a name that is reflecting what the data that is stored in it. So S2 seemed a good name for Sentinel-2 imagery, and also it's short, so I don't have to type a lot. And then I'm putting the EE Earth Engine.image collection, and then I'm giving the name of the image collection. Now, how did I get this one? As I said before, there is a small arrow button here in the search places and datasets input box. So if I click on it, I get view data catalog. If I click on it, I get all types of data that are stored in Google Earth. So I'm going to go to Sentinel. So I have different types of Sentinel imagery. There is a Sentinel-1 SAR, Sentinel-2 multispectral, Sentinel-3, Sentinel-5P. Okay, I want Sentinel-2. And in Sentinel-2 I have surface reflectance and top of the atmosphere. Obviously I want the surface reflectance, and it does have a lot of metadata here. So you have a description, you have the bands, you have the image properties, and this is where you get the cloudy pixel percentage. And you have the terms of use. Okay. Now, what I'm interested in right now is how to get the data. So this is the address of the data. This is the name of the data. So I will copy this part. And I'm going back to the code, and I can paste it here and assign it to a variable. The second line is variable filtered equal S2. The S2 has all the Sentinel 2 level A archive from 2015 up till now stored in one variable. So I'm creating a new variable called filtered, and then I'm assigning the image collection into it, and then applying 3 filters and the median functions. So the filter by date first, and I can pick whatever date I want here from 2, and then the filter by bounds, and I put the area of interest that I'm working on, and I can pick a filter by metadata, filter metadata function, and then I can pick here for my for what I want to do here, I'm picking the cloudy pixel percentage variable of the metadata. But as we saw here in image properties, we have many properties that we can use in our code. And I'm using the operator less than 1%. And then I'm applying a median, so all the values that I'm getting for each pixel, I'm only taking the median to create the resultant image. And last, I'm using the add layer function on the map to add the filtered, which is the result of all these filtrations and median function. And I'm clipping it to the region, and I'm stretching it and ordering the bands that I want to see into red, green, blue. Let's run and see what's happening. So first it's drawing the vector boundaries, and then it's going to put the natural color composite on top of it. So let's comment this map display here and also the vector map display, and go back to the lecture to see step number 2. The third item in the lecture is mapping NDVI for Sharqeya using Sentinel 2 imagery. This is step number 2 in the code, and we start by explaining the normalized difference vegetation index, NDVI. The normalized difference vegetation index, NDVI, is a simple indicator that uses the fact that healthy vegetation has a high reflection value in the near infrared wavelength, while having a low reflection value at the visible red wavelength. And we do that by subtracting red from near infrared values and then normalizing it by dividing the result over near infrared plus red. We end up having a normalized difference vegetation index. This is another way of explaining it. So you have the vegetation, a healthy vegetation, and as you can see, it's reflecting 50% of the energy it's getting from the sun, reflecting it back, while in the red it's absorbing 92% and reflecting only 8%. So you subtract 50 from 8%, you get 0.48, and you divide it over 50 plus 0.08, and you get 0.72. In the case of unhealthy vegetation, you get lower reflectance on the near infrared and higher reflectance on the red, so the value is very small. So this is how you differentiate between healthy and unhealthy vegetation. NDVI is calculated from the visible and near infrared light reflected by vegetation. Healthy vegetation left, this one, absorbs most of the visible light that hits it, and reflects a large portion of the near-infrared light. Unhealthy or sparse vegetation, right, this one, reflects more visible light and less infrared light. The numbers on the figure above are representative of actual values, but real vegetation is much more varied. And this illustration is by Robert Simon. And the source of this vegetation is listed below here. Now, the code for calculating NDVI for Sharqeya province is here in step 2. So first, we extract the near-infrared band, which is band 8 in Sentinel-2, by using the select function on the filtered image. And we store it in a variable. I called it NIR, or near-infrared. And we extract similarly band number 4, which represents the visible red band in Sentinel-2. We use the select function on the filtered image collection, and we store the result in the red band. And then we apply directly the equation. So we have NDVI equal near-infrared minus red divided by near-infrared plus red. And the result of this formula, we apply a clip function on it to clip it just to the region of interest, and we add it to the map viewer. By implementing this code, we get the following image. Now, NDVI produces values that range from -1 to +1, -1 being non-vegetation or water surface or barren land or urban areas and so on, while 1 is lush vegetation or very healthy vegetation. So the white here indicates very healthy and very dense vegetation, while the black would probably be urban area or roads or water surfaces and so on. Sparse vegetation would be in gray. Let's go to the code to see what happens. So I'm going to paste the code, step 2 of the code. So I have a variable called near that I'm selecting the near infrared band and assigning it to it by using the select function over the image collection. And again, I'm using the same function to extract the visible red band and assigning it to the red variable. And then I'm using getting a new variable called NDVI and directly implementing the function near minus red over near plus red and storing the resultant equation into NDVI variable. And then I'm using an add layer function to add the NDVI that resulted from the equation, and using a clip function to clip the result only to the area of interest. So let's run. So this is the resultant image, and you see here a progress bar that shows the calculation progress. And I assure you that if you had a powerful workstation, it would have taken a lot longer than what you have seen here. And we are actually benefiting from the fact that the cloud computing platform of Earth Engine is using a server farm, very high computing power. So what you need is just a good internet connection and you're good to go. You just use all the power of Google server farm in order to produce such analyses that can actually take hours or days if you are using a regular computer. Okay, so you have your NDVI here. Now in the next step, we are going to extract only the vegetation from this layer. Let's go to the lecture and see that. Item 4 in the lecture, which is step 3 of the code, extracting vegetation into a new raster layer. This is the code, step 3. So we want to only extract vegetation. So we create a new variable called vegetation and we assign the image that we have just created, the NDVI image or raster layer, into the vegetation. We implement a mask function to get the vegetation that has a value that is greater than, GTE is greater than or equal 0.3. So we really need to do some trial and error in order to find out the threshold value beyond which everything is vegetation and below which everything is non-vegetation. And then we implement an add layer function on the map in order to add the resultant raster layer into the map. And again, we implement a clip function to get only the area of interest vegetation. So this is what we end up with. So we have a raster layer containing only vegetation extracted from the NDVI. Let's go to the code. So we pasted step 3 code, which is only 3 lines. Let me first comment the add layer from the previous step so that we don't have so many layers added on top of each other. We save some time. So in this layer, in this step, we actually use we start by creating a vegetation variable and assigning the NDVI raster layer that we have created in the previous step into it. And that vegetation, we implement a mask function. And this function takes vegetation greater than or equal to 0.3. As I said before, NDVI values range from -1 to +1, +1 being a very dense green healthy vegetation, and -1 being anything but vegetation, like could be water surfaces or barren land or urban areas. And in between you have all sorts of things. So we need to find a threshold value beyond which everything is vegetation and below which everything is non-vegetation. We implemented some trial and error experiments and we came up with a value of 0.3 as the threshold. And then we implement map.addLayer function over vegetation, the resultant extracted vegetation, and we clipped it by region as we did in the previous steps. And again, this is a progress bar showing the progress. So here, this is a raster layer that contains only pixels that are vegetation. In the next step, we are going to calculate the area of the vegetation. Item 5 in our lecture is step 4 of the code, which is calculating vegetation area. So this is the code, step 4, calculate area in square kilometer first. So we create a variable called area_pxa. You can call it whatever you want. And we use something called pixel area function. Now, pixel area function generates a raster image that contains values of surface area calculation per pixel in square meter using Lambert equal area projection. Now, let me stop here for a minute. If you want to calculate the area of a raster layer, you might want to probably count the pixels and multiply the number of pixels by the area of each pixel or each cell. But that would be the nominal area, because as you know, we are not flat earthers, or so I assume. So we know that the earth is a sphere. So the pixel area near the center of the projection system is not the same as the pixel area furthest from the center of the projection system. So you might have a pixel area that is like here we have a 10 by 10 pixel. So maybe near the center of the projection system, it's actually 10 by 10. So it's 100 meter pixel. But if you go the furthest distance from the center of the projection system, it's probably 99.98 or 0.89 or whatever. So in order to avoid that and account for the difference, we use something called pixel area. Pixel area would generate another raster image that contains pixel values, and the pixel values are the area of the pixel. So each pixel will take a different number, and that number accounts for the projection differences, the error generated by the sphere, the spherical nature of the Earth. So we take that pixel area, so we multiply the vegetation by the pixel area raster, and whenever there is a void, it's not going to get a value. Whenever there is a value for vegetation, it's going to get the area. And then we use a reducer, a sum reducer, in order to get the total values collected for all the pixels in order to get the area. And the area resultant would be in meters, and we use the region, the boundaries of the Sharqeya province as the areas that we want to calculate inside, and we use a pixel size of 10 meters. So area PXA will get us a metric area calculation for the entire region, and then we implement a division function and we divide by 1 million, since 1 million square meter equal 1 square kilometer, and we assign it to area.pxa, and then we print that value with a message. And in our case, area using Earth Engine image.pixel area in square kilometer. So I'm actually being informative. I'm trying to tell whoever is reading this area that this area was calculated using the pixel area function rather than count multiplied by nominal value of pixel. And then I'm actually using another print function in order to divide to print the area in acres or in feddans. And the feddan again is a area measurement unit used in Egypt, and every square kilometer contains 238.0482 feddans. So I'm multiplying the resultant square kilometers by 238.0482 feddans in order to get the total area in feddans. So I have a total area in square kilometer and a total area in feddans. And this is what I get in the side window. So I get the area in square kilometers and the area in feddans. The message is written in Arabic. And this is the value. Let's go to the code and see what happens. So this is step 4, calculate area in square kilometers. Again, I'm creating a new variable called area_pxa, and I'm assigning the result of a multiplication between the vegetation raster layers that we have produced in step 3, multiplied by pixel area raster, which, as I said, the pixel area raster is the value of each pixel area. So each pixel contains only one value, which is the area of that pixel. And that pixel is not necessarily the nominal area. So if it's 10 by 10, it should be 100 meters, but probably the furthest, it's not going to be so because of errors in projection. So it contains the actual surface area of each pixel after accounting for projection errors. And then I'm using a division function in order to divide the resultant area in meters into area in kilometers. And then I'm printing the area in kilometers. And then I'm multiplying by a conversion constant in order to get the area in acres, in feddans, which again is a unit of measurement that is very close to acres. If I run, I get it computing, displaying the image and computing the two areas, the first area in square kilometers and the second area in feddans. As you can see, this is the area in square kilometers and this is the area in feddans. Now, the beauty of this code is that I can go up to the filtered variable and I can change the date. So, for example, let's see if I wanted to compare instead of, now this was calculated for the year 2020, but let's see if I want only for the winter. Let's see if the average per year is less than winter or greater than winter. So let's run it. So That would be the winter from 2019 to 2020. So you see, it took very little time and came up with 3,414 square kilometers, and that is more than 200 kilometers than the average per year. So in the winter there is more agriculture than the average. In the winter is more than the average per year. I can compare 2018 with 2019, or 2015 with 2020, or I can do so many things. So it's very helpful and very efficient if you are writing a report and you want to measure the impact of certain policies on vegetation, for example. It doesn't have to be vegetation. You can do this entire study for water surfaces, for example, lakes or things like that. So that's all what I wanted to say in this video. I hope you found this video interesting, and thank you for listening, and see you next time.